Okay, the second one feels like I've seen this one before. Some people have done this by geometric. I find the easiest way to do this is by divergence theorem, but we'll do it both ways. So if n equals 0, notice that my lower bound is 0. N equals 0, I get 1. N equals 1, I get negative 1. N equals 2, I get 1. N equals 3, I get negative 1. So there's some plus signs here. So that's my series. If you wanted to, you could say the common ratio is negative 1 over 1, which is negative 1. So therefore, the absolute value of r is 1, which is greater than or equal to 1. So therefore, this is divergent geometric because r is actually equal to 1. I don't really like to do it this way, but if you want to do it that way, that's okay. The alternate method I like to do is if n is odd, the limit as n goes to infinity of negative 1 to the n is negative 1. And if n is even, the limit as n goes to infinity of negative 1 to the n is equal to 1. Since the limit does not exist, the series diverges by the divergence theorem / nth term test. Okay, so either one of these methods is fine. Again, I prefer using the divergence theorem situation, showing that the limit doesn't exist because you either get negative 1 or 1 depending upon what n is. And so I'm looking for you showing me that if n is odd, I get negative 1, and if n is even, I get 1. And then saying that the limit doesn't exist, and then diverges by the divergence theorem or the nth term test. Either one of those is fine. So again, show me odd is negative 1, even is 1, limit doesn't exist, diverges by the divergence theorem or the nth term test, whichever one makes you happier. This one just doesn't feel natural to me, but if that's okay if you wanted to do it, as long as you showed me that the common ratio was equal to negative 1 and made some sort of disclaimer that the common ratio is greater than or equal to 1, then you could say divergent geometric and you're all set.